Hello, Gators. Today I wanted to talk a little bit about solutions. And let's go ahead and open this up. So when we're talking about solutions, we're generally talking about when something, often a solid or potentially a gas, dissolves into a liquid. And the most frequent liquid that we refer to is water. So when something is dissolved in water, you have what's known as a solution. Now, just terminology wise, in a solution, what's called the solute is the thing that is being dissolved, whereas the liquid doing the dissolving is known as a solid. So if you put salt into water and dissolve the salt is the solute and the water is the solvent. Now, in terms of dissolving, you generally get the saying that like dissolves like. So if you have a polar substance, such as NaCl, it will tend to dissolve in a polar liquid like water. If you have a non-polar substance, such as like olive oil or something, it will be used to dissolve non-polar things such as butter. So again, non-polar will dissolve in non-polar solvents, and polar solutes will dissolve in polar solvents. And generally, a substance will dissolve if the attraction to the outside solvent is stronger than the internal attraction within the solute. Now, there's a couple ways and mechanisms that things dissolve. One term is solvation. And notice that's not salvation, but it's solvation. And solvation is when the solute particle is actually surrounded by the liquid. And you'll see this with covalent compounds. And I guess once the ions actually break apart in ionic, you would get it there. But covalent compounds such as sugar, so if you have sucrose or glucose and it dissolves in water, the process whereby the molecule is surrounded by water is known as solvation. Ionic compounds tend to dissolve through a process called dissociation. And in that case, you might have a whole block of salt or a crystal of salt, and individual ions will be broken off by the water. So if it's NaCl, you'd get Na plus ions breaking off, Cl minus ions breaking off. And that would be called dissociation, where it's dissociating from the main block of, in that case, salt. Now, you can alter the rate of dissolving by doing things like stirring, or if you increase the temperature, that will affect the rate at which substances will dissolve. And this is just a little picture showing, again, over here, if you have glucose and it's surrounded by water molecules, that would be solvation. Whereas if you have a block of NaCl and the water is actually attracting to, in this case, the minus chloride ion would be, attracted to by the hydrogen, plus portion of the water. And the plus Na ion is going to be attracted with the negative water, or the negative oxygen part of the water. Now, a key term is molarity. And molarity is basically a ratio comparing the amount of solute with the amount of solution that you have. So the technical definition of it is molarity is moles of solute divided by liters of solution. And this is how people generally will measure concentration of solutions. And note that the volume here, liters of solution, is the total volume solution. It's not just the amount of solvent that was put in. Generally, when you put solvent in and then stuff dissolves in it, the volume will increase a little bit. And the units are moles per liter, which is, molar is an abbreviation for that. It's abbreviated with a capital M, or you can just write moles per liter. Now, you'll frequently have problems with molarity. So let's say that you have blood and you find that the blood has 0.0231 moles of Na plus ions in 0.150 liters of solution. And you want to know what's the molarity? Well, like we said, molarity is moles of solute over liters of solution. So it's 0.0231 moles over 0.150 liters, or 0.154 molar. I think we'll just go ahead here. Yeah, so molarity is number of moles of solute per liter of solution. And there's a couple ways you can actually solve this. You can, if you had a problem, you wanted to prepare 500 milliliters of a 0.60 molar solution of NaCl, how much NaCl in grams would you add? You can use the four-step process that you hopefully learned in physics, where you write down your givens, where you have a given of 500 milliliters of solution. You have a given of molarity of 0.60 molarity, and then the given that you're not that's not there is how many moles, which then it has to convert to grams. So the equation would be, again, molarity is moles per liter, or moles would be molarity times liters. And knowing that, since we have milliliters, we can convert to liters, and then molar is molarity. So we have molarity and we have milliliters, and we can calculate moles. And then once we have moles of NaCl, we can convert that to grams. And sometimes it's easier to use dA for this. Let's see if we can move that a little bit. So if you had 500 milliliters of solution, 1 liter of solution over 1,000 milliliters of solution, 0.60 moles of NaCl in 1 liter of solution. And notice we've gone from milliliters to liters. And then using molarity, or moles per liter, we're going from the volume that we have in liters to moles. Then once we know how many moles of salt we have, then dividing 50 or whatever, multiplying that by 58.45 grams of NaCl per mole of NaCl, that will then give us the total number of grams of NaCl, which in this case would be roughly 18 grams NaCl. And let's go ahead. One other term that's worth knowing about is concentrated and dilute. A concentrated solution is a relatively large amount of solute, or powdered drink mix, or chemicals, or whatever, dissolved in the solvent. The concentration is high, and generally it's considered 1 molar or above. Dilute is relatively little dissolved in the water or whatever other solvent you have. Generally it's considered below 1 molar. And you can see, if you have a very dilute solution, it will look really kind of watery. And if it's very concentrated, it will look thick, and light might even barely pass through. And that actually allows us an avenue in which we can use light and use something called spectroscopy to determine the concentration of solutions. As a quick recap, if you make lemonade, what would the lemonade be? Is the mix the solute or the solvent? And hopefully you know that it is the solute. Okay, with this, I'm going to actually, let's escape from that for just a moment, maybe. If I can. Maybe I can't. I guess I can't. So I guess we won't show that until maybe I'll do it afterwards. But what I wanted to get at was that you can, if you have a light, you can basically pass it through a sample of substance. And the more solute that is in that substance, the more the light will be absorbed by that solute, which means that there's a direct relationship between the absorption or absorbance of light and the concentration of a solution. And that's known as Beer's law, where the absorption or absorbance of light is directly proportional to the concentration of solution. And what you can do is actually plot, like if you have known values of concentration, you can see what is the absorbance of these known values. And then by plotting them on a graph with concentration on the x-axis, and in this case it was micrograms per milliliter, and then absorbance on the y-axis, we can make this curve. And what that allows us to do is then use the curve either just visually, or you can write down an equation for the line. In this case, y equals, and it's the mx plus b. So 0.0416x minus 0.0066. So that's the equation for the line. So if you have the absorbance would be y, and you could put that in here and then solve for x and find out what the concentration is. Let's say you had an unknown substance, that was unknown molarity. Once you have your calibration curve, you can then use that calibration curve and potentially the equation for the line to figure out what's the concentration of an unknown molarity solution. So if you had the question of if the concentration is 15 micrograms per liter, what is the absorption? And here we're going the other way from x to y. And you could do it just visually. You could, look here, go 15 up to there, and it would be across, and it would be, a little bit above 0.6 there. Or you could plug in your 15 micrograms per milliliter into x, and then you'd have 0.0416 times 15 would give you a number, then minus 0.0066, and that would then give you y, which would be the absorbance. And in this case, it's 0.62. Now you can go the other way. Let's say you had an unknown with an absorbance of 0.345. What's the concentration? Well, again, we could just go up here and 0.3 is about here, 345 is about there. So you could go across to the axis and or to the line and get to there, and then come down, and you're going to be somewhere in the upper 8 to 9 range for the concentration. And you can also do this, maybe more precisely by putting this value into the y. So 0.345 equals 0.0416x minus 0.0066. So if we add 0.0066 to both sides and then divide by 0.0416, we can solve for x. And I think in this case we got 0.845, which was similar. We said it was in the 8 to 9 range, and it's somewhere right in that range. Right, so I think that's what I wanted to talk about today in terms of concentration.